Throughout the webinar, we will stop the presentation to review. There will be multiple choice poll questions which you will be able to answer in the sidebar. Please go ahead and answer these questions as they come up. You will have about 1 minute to answer the question before we go over the answer. During the webinar, please feel free to use the chat window to ask questions and discuss the topic. We will take time after the presentation to answer these. This and other recorded webinars will be available to WePass subscribers. Register through wepass.com to become a subscriber. Today's topic is titled TG142 Tips, Tricks, and Modern Techniques, presented by Justice Adamson, Assistant Professor of the Division of Radiation Physics and Department of Radiation Oncology at Duke University Medical Center. Thank you for joining us, Justice.
All right, so today I just got this presentation that we're going to go over TG142. So first, just give an overview of what's in the report, some of the things it covers, some of the background, and then also some practical strategies for applying it. So lots of useful references out there. This is just a subset of many, I would say, that are available and have useful information regarding the report. All right, so a little bit of background. This report came out in 2009, and it's basically on the quality assurance of medical accelerators. And so at that time, it was actually an update to a prior report, which was TG40 from 1994. And so basically they were charged to update this, the task group was charged to update this table from TG40 and add some recommendations for things that had been developed along the way. And these included asymmetric jaws, MLCs, dynamic virtual wedges. And then what the actual report includes is also not only added recommendations for asymmetric jaws, MLCs, and virtual wedges, but also imaging, integrated imaging, and it gives some new tests and tolerances. And one of the big differences is that these tolerances are now specific to the types of treatments that are being delivered for the machine, whereas TG40 kind of gave one-size-fits-all recommendations for any linear accelerator. Now it's broken down into non-IMRT, IMRT, and SRS, SBRT linear accelerators. And the overall goal that's being sought after is that the dose be delivered within plus or minus 5%. So when these QA recommendations are given, it's basically so that you can be able to have your machine deliver dose within that amount, which means that each individual component needs to be smaller than that so that the overall uncertainty is within plus or minus 5%. And another thing to make note of is a lot of the measurements here are relative to baseline values. So when a machine is first installed and it's commissioned, there's a lot of commissioning data that's acquired, and a lot of the QA is relative to that data that was first acquired. So you're seeing, is it the same as when we prepared the treatment planning system with the data for this machine? Are we getting the same profiles, the same everything as before? So a lot of these things are baselines based on commission or test relative to the baseline. A couple of caveats about TG142. So a lot of questions are, do I have to follow everything in TG142? So TG142 is geared to be flexible for the physicist to customize the QA program to the individual clinical utility. I mean, one thing that's very clear with the dividing it into different types of uses of the machine. The report itself states, the recommendations of this task group are not intended to be used as regulations. These recommendations are guidelines for qualified medical physicists to use and appropriately interpret to their individual institution and clinical setting. Each institution may have site-specific or state-mandated needs and requirements, which may modify their usage of these recommendations. So one thing to take into account is that this report was published in 2009, and there's been a couple of techniques that have been developed since then that should also be included in a modern QA program, and so that would not be in this report. Some examples would be VMAT was not really part of this report, and so some other things as well. So it's really up to the qualified medical physicists to account for these in their own specific institution. So I also wanted to mention another report that's recently came out. This is the Task Group 100 report. And this is somewhat related because they also go over QA and methods of developing QA and risks and tests and tolerances. So TG100 is really an application of risk analysis methods to QA. And one thing that is interesting is that method isn't necessarily going to give the same results as the recommendations from TG142. And you can see that here. This is a table from TG100, and it shows you if you go through this kind of risk-based analysis, you can get a certain frequency for certain tests, and that may very well vary from what is recommended in TG142. But in this presentation, we're just focusing on TG142 and not really going to look anymore at TG100. All right, so here's our first question.
All right. Hello, Justice. Can you hear me?
Yep.
Okay, great. So the poll is just loading up now. So for those of you who haven't had a chance to do one of our webinars before, you can just go ahead and find the poll on the sidebar of your screen, and we'll give you about a minute to answer this poll question. In the meantime, maybe you can just go over the question, Justice.
Yeah, so the question here is it's true or false question. TG142 recommended frequencies and tolerances are based on the risk analysis methods outlined in the Task Group 100 report.
All right, thank you. So we'll just give everyone about 30 more seconds to go in and weigh in on this poll. I see answers are still coming in. Okay, so Justice, if you could go ahead and go over the answer, that would be great.
All righty. So the answer here is false, which it looks like most people got. So the tests and tolerances developed using the risk-based methods in TG100, basically TG100 covers the risk-based method, and that may very well vary from what the recommendations are in TG142. All right, so moving on, a few more caveats with TG142. The task group itself doesn't really describe any experimental techniques. They give a lot of references, or I should say they cite a lot of references to methods to do that. So it really only covers the recommended tests and the tolerances, but doesn't really give you methods to do that. But we'll talk about a few of those here and give some brief examples on how those tests can be carried out, and in a hopefully a somewhat efficient manner. There's also an upcoming related task group to be aware of, which is TG198, and that is this task group is supposed to come up with an implementation guide for TG142. So their charge is basically to develop some specific procedural guidelines and also come up with maybe some sample daily, weekly, monthly QA. So that hasn't come out yet. I recently checked the status of that task group, and basically they're in final writing, and so that may be coming out soon. All right, the other thing to note here is that the task group gives tolerances for these tests, and something to think about is what happens when something fails tolerances. And there's three really action levels that they go over. The first level would be something that, if you see something that goes over and it's maybe once in a blue moon, or it just happens, it's irregular, it's maybe not a trend that you've seen, and it's very close. Maybe it's still under the tolerance, but it's or close to the tolerance. So that level would be kind of an inspection level, where the next level for something that may look more or be more severe would be some sort of a scheduled action. So, but that treatment continues. And then the level 3 would be something that is a big change, something that should never be treated. That would be a level 3, which is stop treatment and immediate action. So there should be some thoughts here, especially with QAs that aren't being carried out by the physicists themselves, like maybe the daily QA, as to what levels, what action levels should these tolerances be set at. All right, so let's move on to some specifics. So we'll go through the tests and tolerance requirements for daily, monthly, and annual QA, and then I'll also give some example QA routines. And the QAs I'm going to give, the example I'm going to give is really for a linear accelerator with MLC-based IMRT, with physical rather than a dynamic virtual wedge, and with onboard KV and MV imagers and KV cone beam CT capability. All right, so daily QA. So this is the table taken directly from TG142 report. And a couple things here to note. You can see on the right that those tolerances are broken down by the use of the machine, non-IMRT, IMRT, and SRS, SPRT. One thing that I was surprised when I went and looked this closely is that the electron output constancy is only is specified as being a weekly check, whereas I've never really heard of it being done on a weekly basis. I've always seen it as daily, but so that I found that a little bit surprising. But there's basically some dosimetry tests here, mechanical tests, and safety tests. And then also there's another table here, and this one, which is the imaging tests. So there's also imaging tests that are recommended for daily on a daily basis. And as you can see here, basically you're giving the same test for each type of machine. It's just what your action tolerance is changes based on whether it's an SRS SBRT machine or non-SRS SBRT. And then there's also some recommendations for MLCs and for the virtual and dynamic wedge. So MLCs, it's recommended to do a weekly qualitative test and a functionality test for the virtual dynamic wedge on a daily basis. All right, so here's an example daily QA procedure. And on the right here, I've got a bunch of different types of daily QA detectors. I didn't want to just endorse any one because I think there's a lot of good vendors and a lot of good equipment out there and a lot of good options. So first off, this is just kind of an example. Daily QA would be, have a procedure where whoever does that first aligns the daily QA measurement device using the light field and the optical distance indicator, and then verify the light field jaw positions. So that takes care of some of the mechanical tests. If I back up a little bit, you can hear some collimator size indicator here. So that basically you're doing some of your lasers and light field and collimator tests as part of setting up your daily QA device. Insert the graticule and verify the alignment if it's a non-image guidance machine. Check the laser alignment with the daily QA device, set the MLC size, verify that, verify the door interlocks that prevents beam on, check the warning lights, the video monitor, the intercom, deliver the output and verify that for all photon electron energies. Then once again, this is an example here, and as I mentioned, actually states weekly in the report, but we do it on a daily basis here. And then run one dynamic wedge to check functionality. And I added that in. I said that we were only doing physical wedges, but it's there. Anyways, one thing that's interesting here is only step 8 is what you would, if you think of a daily QA, usually you're thinking about the output check, but that's really only one of many steps here that are being checked. So the output is important, but it's not everything that happens for that daily QA. All right, and then this is some examples for the imaging side. So that didn't really even include any of the imaging. So set up some sort of a daily imaging phantom using lasers and light field. Test the imaging collision detectors and the door interlock. Image the phantom. Measure and record the distance of the central BB in the phantom to the isocenter. Apply a known shift and verify, and then acquire a cone beam and shift back and verify. So this is what this looks like. Basically, set up this cube to the lasers, image your planar imaging, some orthogonal imaging, then shift based on that, take a cone beam, and then shift back. So here you can see the cone beam is acquired at the shifted position, and then shift back and verify. So this way, using 2 shifts, but 2 types of imaging, you can verify both your orthogonal planar imaging and also your cone beam CT on a daily basis. All right, another question here. True or false, the TG142 recommendations for daily QA does not include any imaging tests for non-SRS SBRT linear accelerators.
All right, great. Thank you, Justice. So the poll is live now. If you haven't had a chance to weigh in, please go ahead and find the poll loaded on your sidebar of the window here, and we'll give you about a minute to weigh in for this question before we go over the answer. And also, I just wanted to mention, it looks like some folks are having trouble with their connection. So this webinar will be recorded, and it'll be available on our YouTube WePass YouTube channel up until Monday. So you can, if you're having issues, you can come back to our channel and view it there. And we'll also have it recorded for longer than that on our wepass.com website. So if anyone needs to come back to this webinar at a later date, we will have it recorded. All right, Justice, if you want to take a moment to go over the answer, I think now would be the time.
All right, so once again, looks like most people got that. So false, the same daily imaging tests are recommended, but with stricter recommended tolerances for SRS SBRT linear accelerators. All right, so let's move on to the monthly QA, which is where a large bulk of the QA falls for the TG142 recommendations. So first here, this is the recommended mechanical tests. So there's a lot of things in here. Just to point out a couple things here. The lasers are on there. It's really good to check those early before you're checking other things, just so that you can trust that the lasers are correct when you go to do your other tests. The light field, radiation field coincidence, and jaw position indicators, crosshair centering, and treatment couch position. Those are good to group together. They use a very similar geometry or the same geometry. You can use a field size jig or combine, and then these can also be combined with some of the imaging tests. Crosshair centering and treatment couch position indicators, that may be best done with graph paper, something where you can see the distances with the light field. All right, the symmetry tests recommended on a monthly basis. So this is the table from the TG142 report. A few things here. The X-ray output, electron output, and the dose rate output constancy, those can typically be measured with typically is done with an ion chamber relative to baseline, and those would be this would be an ion chamber measurement with a temperature pressure correction, and then that would be relative to a baseline that was taken at right after the absolute dose calibration was done at commissioning, and either reset on an annual basis or at least verified on an annual basis. The backup monitor chamber constancy, so that's basically just observing the difference between MU1 and MU2, your two monitor chambers, to make sure that, because one of them is what's going to set your output, the other one is just a backup, just making sure that they're still in line with each other. The profile constancy, this can be measured with ion chamber or diode array, and it can potentially be measured with some daily QA devices. However, I would suggest that the physicist takes a close look at the sensitivity of the device to make sure it's sufficient to meet the tolerance. The 1% there is a pretty tight tolerance for beam profile constancy. And then electron beam energy constancy is also suggested. So this is often also measured by a daily QA device. Otherwise, you could use a ratio of output at two different depths. Surprisingly, what's not in this table is a photon energy constancy, which was included in the older TG40 report. So another thing here to look at is that, or to point out, is that these are constancies for these profiles. This is not saying that the flatness and symmetry of the beam has to be 1%. There's a flatness and symmetry equations provided in a couple of different places in the reports and so on and so forth. And there can be the confusion that the beam has to be within 1%, but less than 1%. But really what this is saying is it should be within 1% of the baseline that was acquired at commissioning. All right, so imaging tests and tolerances for monthly QA. A few things to point out here. The imaging and treatment coordinate coincidence, and also for both the MV and KV, those can be done with a cube phantom, maybe even at the same time. The scaling can be done at the same time as the light field and radiation field coincidence if you're using a jig that has distance indicators. So those can all be combined. And then all the image quality things, usually there's going to be some sort of a specific phantom, a phantom that's specific to that modality that will that can measure these things, and then you just take a baseline at commissioning or at annual and then compare to that baseline each month. And then uniformity and noise, that can probably be best done with just an open field for the planar imaging. For the cone beam, it's best done with some sort of a phantom that has a uniform density. All right, so other tests and tolerances with the monthly QA. These include some safety tests for laser guard, and then gating and MLCs. So the beam output constancy is one thing that's recommended to be tested on a monthly basis. So this makes sense to do when you're doing your other output constancy checks. So while you've got your solid water set up and you measure the charge and relative to the baseline, for your energies, you can also do the same thing with gating and just get an integrated charge. And for the MLCs, so some of the things that are suggested here, it's travel speed and leaf position accuracy. So those, in my opinion, can be done pretty well with a portal imager and use some specifically designed IMRT fields to test those things. All right, so let's do an example, just go through an example of monthly QA. So starting with the mechanical QA. So first, you could test gantry and collimator angle indicators at cardinal angles, ODI versus front pointer, do your lasers, check the coincidence with the front pointer, and check the coincidence with the imaging cube, with some sort of an imaging cube phantom. Then check the patient support assembly, the couch angle, the couch lateral, longitudinal, and vertical motion, the collimator crosshair centricity, and then the jaw and MLC field sizes, light versus radiation fields there. I have MLCs in there. I don't think that's actually in the recommendations. We do it here, and so I threw it in, but I actually don't think it's in TG142 for monthly. Although it does have some other MLC tests, and I guess you can make the argument that this is meeting those. MV planar image scaling. So there's one of the imaging tests thrown in there with the mechanical, and then accessory checks. So testing some sort of that your accessories and the interlocks work. So a couple of notes here, just for speeding things up. One thing to think about is it okay to alternate your going one direction versus the other per month for your gantry and collimator angle indicators? Maybe, depending on how comfortable you are with that. Also, ODI, checking at multiple distances, maybe 100 cm and then maybe 80 or 120, maybe alternating those two. And then accessory checks, probably at least one wedge and one cone per month, possibly. So just a couple of thoughts there. So here's some examples of what this looks like. So here on the left is checking the ODI relative to the front pointer. So I've got the solid water on there because I know that solid water is 20 centimeters, so I can use the front pointer, check the ODI, and then pull the solid water out of the way, pull and check the ODI at 120 as well. And then also you can do your lasers versus the front pointer. There I've just thrown up a piece of paper so you can see the lasers and the coincidence with the end of the front pointer. And as you rotate the gantry, you can kind of see the coincidence there and see how your lasers line up as you go around. And then you can also check with the cube phantom as well. So basically, you'd line this up with your light field in both axes and check how's your lasers align with that. And then some sort of either graph paper, or here's a jig that has, you can't see it very well, but it's got a grid on there so you can see each millimeter. And so this is good for testing your couch motions and the couch rotation and collimator centricity. So as you rotate your collimator around, does your crosshairs, do they stay within the tolerance? All right, light field versus radiation field and planar image scaling. So this can be done with some sort of an imaging phantom here. This one has some radiopaque markers you can see here, and you can just test to make sure that your scaling lines up, that where you've set up your light field, that it coincides with where your digital graticule is, so on and so forth. All right, so let's move on to the dosimetry portion of the monthly. So you can start with output measurements in solid water. And this should be done with temperature, pressure corrected, and get some sort of a charge reading relative to an annual baseline. And at some appropriate depth that is set at baseline. And then also measure output during gating for one energy. And that can be alternated monthly perhaps, where you just gate and you get the integrated dose or integrated charge and compare that to what you got without gating. And then also running the daily QA device and just reviewing the daily QA results, and then measuring basically your output, your off-axis output constancy and electron energy constancy using that device, or another device that might have a better resolution. or maybe more sensitive to those tests. All right, so moving on to the monthly imaging and MLC QA. So as an example, do picket fence at cardinal angles, acquire portal dosimetry for some sort of a leaf motion shape, and check that, do a constancy check of that relative to a baseline, check the imaging collision indicators. For MV and KV planar imaging, do uniformity and noise, and then spatial resolution and contrast with a specific phantom to each of those. Scaling, so scaling is already really done with the MLC, the megavolt, the light field, but the KV either should be done when you do the light versus radiation field as well, or do with at this point. And then do comb CT QA, which my suggestion would be to use some sort of an all-in-one phantom that will test geometric distortion, spatial resolution, contrast, Hounsfield unit constancy, uniformity, and noise. So you just get one scan, and that you could then, after the fact, go back and analyze that image and get all of these at the same time. And what we do here is we have probably 4 or 5 different clinical templates that we use for cone beam. So we have like a head setting and a pelvis setting, so on and so forth. And then we will just alternate which one we test each month. So we will test one a month, and it just alternates. That way they all get tested over time, and we're testing we're testing the CBCT system every month. So here's an example for picket fence at cardinal angles, and we just have this fluence pattern here that is delivered with sliding window IMRT, and we just acquire it every month, and we just compare it. We do some sort of an analysis to compare the two, and we see how that is relative to the baseline. So MV, KV uniformity and noise basically acquire an open field measuring uniformity and noise. We do some calculations there to calculate that based on image. The MV and KV scaling, so just using some sort of a jig there that has those again, and measure the field size. So MV and KV spatial resolution and contrast. So on the left, that's a phantom that is specific to megavoltage planar imaging, and it has these drilled points that have different depths and different widths. So you're testing a combination of spatial resolution and contrast. On the right is a phantom that's specific to KV imaging, and it has the low contrast inserts there, and then a high contrast, the spatial resolution line patterns in the middle there. So, and these are just 2 examples of many great phantoms that are out there, and that could be used. So there's there's 100 different ways that this could be done, and with different phantoms, and there's a lot of options. It's just a matter of choosing one and getting a baseline and just comparing to that. And here's an example of a cat fan that we use that has basically an all-in-one for cone beam CT. So basically, there's these different sections of the phantom, and you can see here on the left, one of them has some in these points here, and we measure the distances, checking for geometric distortion. It has a high contrast or a spatial resolution, line bars that we can test. It has Hounsfield constancy, and so on and so forth. So we can test everything here with one thing. And again, there's other phantoms out there that can equally do this equally well. All right. So another question here.
All right. Let's see, we're starting the poll. So for those of you who are just joining us, you can go ahead and answer the poll in the sidebar. We'll give everyone about a minute to go ahead and weigh in on this poll question. And I just wanted to also announce that we'll be sending out an email with the link to this recorded webinar on our YouTube channel. So if anyone is still having issues with their connection, please go ahead and check out that email that'll be sent out later today. And Justice, I wanted to draw your attention to the chat. There are several really great questions. I don't know if we'll have time to go over all of them, but maybe you could pick out a couple that you think you could get to either briefly now or at the end of the presentation.
Yeah, I think we should probably go over them at the end just to make sure we get through everything. But then I'd be happy to go through them all.
Okay. All right, so you can go ahead and review the question and the answer. I think most people have had a chance to weigh in.
All right, so the question here was true or false, the TG 142 recommendations do not necessarily require that the flatness and symmetry of the beam profile be less than 1%. And the answer is true. Absolute flatness and symmetry does not need to be 1%. Rather, the profile is recommended to be within 1% of the commissioning data or the baseline. All right, so let's move on to annual QA. And just a note here that these tests, they're mostly in addition to monthly tests, right? Because you're already testing all this other stuff on a monthly basis. So here we're looking at a lot of the annual tests, the stuff that's done in addition, but only on an annual basis. So this table here shows the mechanical and gating tests and tolerance for annual. And a couple of things I'd like to point out here, and just, the ease of carrying this out. Collimator rotation isocenter and couch rotation isocenter, those can be done with graph paper, the same setup basically. Tape a piece of graph paper to the table and rotate those. The coincidence of the radiation and mechanical isocenter, so that's basically your star shot, but that'd be done with film or portal imager where possible. Gantry rotation isocenter, that can be done with the front pointer. The beam energy constancy, this is solid water integration charge at 2 depths. And this is for gating here. So this is basically checking this. This is kind of like a monthly test, but doing it with gating. And then temporal accuracy of the phase amplitude with the gating on. So some of these tests, so this one I would suggest doing where you just take an image where it's a gated image, and you see the position of your phantom that is used in gating, if you're using some sort of a amplitude-based, like RPM system. All right, dosimetry tests. So there's a huge list here, and so let's just break it down into what's on it. So a lot of this is done with a water tank. So you have, or it can be done with a water tank. So your flatness and symmetry change from baseline. Electron flatness and symmetry change from baseline. Your output TG51, the absolute dose calibration, that's in the water tank as well. And then your beam quality and electron beam quality. So those are basically acquiring your PDDs. So all of this can be done in the water tank. Some of the other tests here: spot check of field size dependent output factors for electron applicators, physical wedge transmission, X-ray monitor unit linearity, electron monitor unit linearity, and X-ray output constancy versus dose rate. So those can all be done with ion chamber in solid water, or if you already have the water tank, you could in theory, do those in the water tank as well. Many of them. X-ray output constancy versus gantry angle. So here, this would, and the output, electron output constancy versus gantry angle, and then the off-axis factor constancy versus gantry angle. The first two here could potentially be done with something like an ion chamber at the isocenter, or doing all three of these together could be done with something that either mounts to the ion chamber or mounts to the gantry, so that you're always measuring relative to the gantry, or it could be done I've seen this done by just putting one of these devices on end so that it's up, and when you have the beam at 90 or something. And then some of these other tests, like the arc mode and the SRS rotation mode, those might not require any extra equipment and just using the outputs given by the machine. All right, MLC, annual MLC tests and tolerances. So it's recommended to measure the MLC transmission. So this is the average of the leaf and interleaf transmission. So typically, you'll already have measured leaf and interleaf separately for commissioning, but to get an average of those for all energies, so that can be done with something that's just big enough to kind of average over those. So maybe like a large ion chamber. And the MLC spoke shot and coincidence of light field and X-ray field can also be done together with film or separate with an imaging jig for the coincidence of light and X-ray field. Leaf position repeatability and segmental IMRT step and shoot tests. So those can be done maybe with a portal imager or some sort of an array that measures your fluence to test some of those things, or film. Moving window IMRT, again, this can be done with the portal imager, which is very convenient if you're measuring it at different angles. And one thing to note here that I was actually surprised when I read through this carefully was the recommendation here to check light field and X-ray field for all energies for MLCs. So some of the imaging tests. So basically, if you look at this here, there's nothing substantial here beyond the monthly other than dose and I guess beam quality for planar imaging. And there's no tolerance difference here between SRS and non-SRS machines. All right, so we'll just run through a couple of examples here. So gantry rotation isocenter, collimator and couch rotation isocenter. You know, you can use a front pointer here and some sort of graph paper for this test here, followed by star shots. So basically, you have some film. You put your jaws very small, and you deliver a bunch of monitor units, and so you get this sort of star shot. And there's programs that can analyze these and see just how much wobble there is in each of these axes. So for annual QA, there's lots of different water phantoms out there that can be used to measure basically these components that are done in the water phantom. The photon, electron, flatness, and symmetry, basically profiles, your absolute dose calibration, your X-ray and electron beam, or photon and electron beam PDDs. And just some notes on the detectors there to be used for this. There's clearly you'll want an ADCL calibrated chamber when you're in an electrometer when you're doing absolute dose calibration for TG51. And then for the profile and PDD measurements, ideally some higher resolution detector, and ideally the same as your baseline so that you're measuring apples to apples. So I just wanted to throw this out there as maybe a possibility for an alternative annual dosimetry QA. So you could actually, if you didn't want to bust out or to use a very large tank and do all of those at the same time, and you have the correct baselines, it may be possible to do your TG51 calibration in a small water tank, one of these ones that just measures in one axis, and measure your PDDs there as well, and compare it to baseline, and then compare your profiles using one of the many arrays, either ion chamber or diode arrays that are out there that can measure. So some of the other things that were on there, which can be done either in solid water or in a water tank, would be, and basically it's very simple setup here of an ion chamber in solid water. Your photon electron output factors, wedge factor, mu linearity, output versus dose rate. So for the output versus gantry angle, one possibility is to put an ion chamber at the isocenter with a buildup cap, and then rotate your gantry and get different outputs for a small field. And then for electrons, you could do it you could do it with solid water, and then you just rotate your solid water taped together and get it at 90 and 270, or probably much easier using some sort of a gantry mounted or rotatable detector. And one thing to note is that if you're already going to use some sort of a gantry mounted detector, then you can do maybe those at the same time, because it's also recommended to do flatness and symmetry at cardinal angles. All right, so MLC QA, that's recommended on an annual basis. So just an example here would be, starting by using some large ion chamber in solid water at central axis and measuring, or in the water tank, for that matter, measuring MLC transmission, averaged MLC transmission through the leaves. And so to do that, basically measure the ratio of dose with the open field in the same jaw settings, to the same jaw settings, but with closed MLCs. And then one note there is just to deliver sufficient monitor units to get a signal for the closed field. Doing an MLC spoke shot, that can be done with either film or the portal imager, along with collimator, couch, and gantry star shots. And then MLC light versus radiation. Basically, this is very similar to the monthly test for JAWS, but you can use an imaging jig with fiducial markers. So testing the repeatability for step and shoot and dynamic or sliding window IMRT, basically very similar to monthly tests. All right, so for the annual imaging QA, one thing to note with this is that some state regulations mandate specific measurements for imaging dose. So I've got here some pictures of this kind of aluminum setup here with the detector below it. That's all basically. I don't think there's not very many details about how to measure this in the task group. And one of the first places I would go is honestly to see what the state or regulatory body regulations are for imaging dose measurements. But what we do is we basically have a device on the left here that will measure dose and also beam quality, and we do that on the annual basis for our KV planar dose, and then for imaging for the cone beam, our CBCT dose, what we do, what I do is use a CTDI phantom. I actually am not a huge fan of using a CTDI chamber with cone beam because the large length of that ion chamber is really meant for a diagnostic CT, but it gives a constancy check as long as you're not getting some sort of partial volume effect on the edges. There's also some other phantoms out there. I've got one of them up here that allows for some TLD inserts. It's a CBCT phantom, so that could potentially be used. I could see that being used, or you could even use a farmer chamber that was, or even one that was the ADCL will even give you a calibration in that range if you really wanted an absolute dose to compare to. All right, so the other thing to note is after the annual QA, especially right after absolute dose calibration, any output baselines, for example, for your monthly, should be at least verified after you've done that, especially for daily and the monthly outputs. And then any other baselines, whether, especially if there's been any changes that were made during the annual QA, just to verify those baselines. All right, last question here.
All right, great. So the poll should be loaded. If you can go ahead and find it on the sidebar of your window. We'll give everyone about a minute to load the questions, and then I guess after this we can go right into Q&A. And would you go over the question?
Yeah, so the question here is, MLC light versus radiation field is recommended to be tested for all photon energies, true or false?
Okay. So we'll give everyone just a few more moments to go ahead and weigh in on the poll question here. All right, Justice, I think we can go over the answer. It looks like most people have had a chance to weigh in on the poll.
All right, answer is true, which honestly, that was surprising to me when I read through the report carefully, but that was their recommendation. All right, and that's all of the information that I have. If we'd like, we can go over maybe some of the questions.
Yeah, if you could go over to the chat area, there's some really great questions posted up there, and we can quickly, we might not be able to go through all of them, but maybe we could just pick a few.
All right. So let's see. So one question here is, what exactly does 2% 2 millimeters for electron beam energy constancy mean in practice? There's a lot of great questions here about the tolerances, and I think that's where things get a little bit tricky. And I think so if you think about an electron PDD, you have an area where the dose is somewhat flat, especially for higher energy electrons, and then you get some sort of a fall off. So and sometimes that's a very sharp fall off there at the end. So I think the 2 millimeters is probably referring to your R50, and I don't think you would expect your dose on that 50, where you've got where the dose gradient is going down very fast. I wouldn't expect that to be within 2%, but I would because you've got such a high gradient there. But I would expect your R50 to be within 2%, where you're falling within, or it's not 2%, 2 millimeters, where the dose is kind of falling off 2 millimeters. All right, here's another one. Is it expected that if your monthly flatness symmetry is off by 1.5% from baseline, that you should bring someone in to rebalance, or should you keep an eye on it for a couple of months? That's a good question as well. We talked in the beginning there about the action tolerances and how, there's these 3 levels of, just inspection and monitoring it, scheduled maintenance, and stop, where you stop treatment and until you fix the problem. So if I was doing monthly and I saw that it was off by 1.5%, the first thing I would look at there is, I'd first check to make sure that I didn't have some issue with the measurement equipment. And if I was confident that there was an issue, so I guess it depends on whether it's photon or electrons, because I wouldn't expect to have a real flatness problem for photons without seeing also a change in energy. So the first thing I would do is probably investigate further to make, maybe a more detailed profile measurement, so you get the full profile and compare that. And if I really did see what would be probably most common would be some sort of a symmetry issue, I would probably correct it. If it was symmetry, so you've got one side off then from the other side, then I would probably correct that, especially which you would expect if your commissioning data had a symmetric beam. So you would expect at commissioning you had a symmetric beam, and if it was off, that's something that is probably not terribly uncommon, or I would say unexpected. And so I would probably tune that back to the commissioning. And ideally, you'd have some sort of either the water tank or some sort of profiler or something that could measure, some array that could measure that profile. And if you had a baseline, you could just compare it to, so you could tweak it back. And then if I was to tweak it, I would definitely check output after the fact. All right. There's another question. How are some tolerances like 1% assigned? I understand the rationale for wanting the sum of the errors to be less than 5% dose error, but why choose 1% as opposed to 1.5% or 0.5%? Is this based on the limitation of the equipment and inherent accuracy of the test used? I think another good question. I think it's probably a combination of both. Honestly, I was not involved in how those were chosen. I would say that the first concern there is how much of a dose difference is this going to make for a given patient. And if it's an SRS or SBRT patient, then they have very few fractions and a very tight fall off. So that's one reason why you see some tighter tolerances there. Whether there was an error analysis that went into that to see what percentage error was allowable to get to 5%. I'm not entirely aware. And I would say that when you do these tests, you do have to look at what equipment you're using and the inherent limitations that they have. That's definitely something on the physicist, individual physicist, and you definitely should take into account.
All right, thank you so much, Justice. Did you have another question you want to answer? We still have another minute.
Sure, I'll just answer one more here. So why is couch position tolerance tighter for SRS, SBRT, but gantry and collimator angle tolerance is not also at 0.5 degrees? That's a great question. So the answer is, when this came out, the most linear accelerator-based SRS was done with cones, and so collimator angle was not really an issue. And gantry, they're typically done with arcs, and so a little bit more on the arcs, it's not going to make a big difference. But actually, there's a paper that we recently published looking at this for when you're doing more MLC-based SRS, and especially if you have any of that target off axis. And we found that probably, especially for collimator, it should probably be tightened down to 0.5 degrees for some cases like that.
All right. If there are any other questions, it looks like we still have some time if you want to go over them, or we can wrap it up.
Sure, I can keep going over some of these.
Sure.
Here's one that's interesting, I think. If I calibrate my profiler for dose, do you think it is a legitimate device to use to check output instead of solid water? I've been actually thinking about that for a while, because in theory, it has an absolute dose calibration. And so you could do your flatness and symmetry and your absolute dose all in one on a monthly basis. I do think it's really nice to have a baseline calibration with an ion chamber in solid water, because it's a simple setup. You know what kind of there's not too many variables that can go wrong that you don't have control over. So at the very least, I think I would want that to have as a backup in case if I saw something with a profiler that I was using for not absolute, but a monthly baseline check of output. I would at least want to have a backup. I could go to my ion chamber and verify that it was off. I don't think I would want to tune the beam, or tweak the output based on a profiler. But I think it's a good question, and I'm not going to say yes or no, but I would probably want at least a backup with an ion chamber. Do you use a copper filter when you use your leads KV test object? A little tricky with the TrueBeam capacitance touch guard over the KV source. Yeah, that's actually true, because with the 2100s, it had a copper insert you could just put in. We actually do not, for that very reason that Anu pointed out there. And instead, we've just changed our such that we don't saturate the image. And so it's not. I don't know if it's ideal, but it's what we do. Do you have a good way to evaluate the picket fence images if you don't have analysis software like DoseLab? That's another good question. There's a lot of good softwares out there like DoseLab to do some of these analyses and automate them. As part of the commissioning tests for MLCs, one of them is actually to deliver a picket fence with a leaf that's off, just to verify that you can see the difference. So I would say at the very least you could deliver something like that and see, okay, if I have a leaf that's off, how much can I actually visually see? And so, I mean, if you know that you have a certain tolerance and that you can visually see the difference from the portal imager to within some level that's at the tolerance level for your test, then you may be able to get away with the visual test. But obviously, it's better to have some way to if you have it. All right, I think probably there's a lot of questions here. I don't know if I can go through all of them, but.
All right, well, thank you so much for going over those questions, Justice. We'll be sure to put those questions up on the wepass.com website for test questions. So if anyone isn't a subscriber already, please be sure to go over and check out wepass.com for test questions, for other live recorded webinars, and more test prep tools that you can take advantage of. And thank you all for joining us today. As I mentioned, this and other recorded webinars are available to subscribers at wepass.com if anybody wants to become a subscriber. And if you'd like to join us for our next free webinar in the series, it'll be on surface-guided radiation therapy on Thursday, March 30th at 6:30 p.m. with speaker Mike Talhammer, the Chief of Radiation Physics at Centura Health. And for up-to-date information about upcoming webinars, you can follow WePass on Facebook, Twitter, and Google+. And if you'd like to recommend a future speaker, you can contact me directly via email at christina@wepass.com or by taking this short survey. And thank you again, Justice.
You're welcome. Thank you.